Thank you, everyone, for the patience and for joining. For the people online, it's so great to see so many of you here. So this is the second installment of the Energy Systems Seminar. My name is Emil Dimenchu. For those of you who don't know, Stefan Bacher is my co-organizer who, now you saw him, putting out this fire here, and so it's very good to have him as well. So yeah, today we have the pleasure to hear from Sigurd Bjarghov, who is a PhD candidate in our group in Markets and Systems in Electric Power Engineering. Sigurd has published quite a bit in the area of electricity markets and distributed resources. So it's great to have him share his insights with us today. And without further ado, I'll let him take over.
Yeah, thank you, Emil. I'm so happy to have this big seminar back. I think it's been 2 or 3 years since it closed before Corona, and it was one of my favorite times of the week. So it's a great honor to be back. So that's a lot of fun. Actually, in my PhD, I started working quite a lot on local electricity markets, and I even started with peer-to-peer markets. But I'm slowly transitioned more and more into grid tariff design and not really peer-to-peer markets anymore, because I'm an electric power engineer. I want to focus more on the grid aspects. So this is sort of a wrap up of the things that I've been working on in my PhD. And I thought that instead of just presenting a paper I published something, I tried to make it a bit broader. Hopefully it makes it more interesting for you, and it helps me to prepare for my thesis writing. So that's the general idea. And the reason I've been moving more towards grid tariffs is because we care somehow, because it costs us a lot of money. Actually, it costs us 20 billion just for the DSOs per year. And that's only in Norway, right? And the TSO also takes roughly 10 billion a year. And this totals to almost 30 billion, welcome, 30 billion NOK a year, which is a significant amount of money that is paid every year, that has little or no incentive for grid-friendly integration of consumers. So that's why we're looking into this, and it's a pretty big part of the electricity bill, and why not look into how it can be shaped more fair, more effective, etc., etc. So that's the reason why we care. So I'll talk a bit about what the hell are they, how to design them. Some of the cost redistribution things that could come when you change the design. Some people will pay more, some will pay less. Is it right? Is it wrong? The importance of coordination. It's not only about making a price signal, it's also about coordinating the assets that we have to actually make it grid friendly. And then I wrap up with some takeaways. And I have some bonus slides, maybe we'll get to them, but let's see. So NVE, the Norwegian regulator, decided, I don't think like 10 years ago, that we want to start looking into a change of grid tariffs. And the idea was to move from energy-based volumetric flat tariffs that we have today to capacity-based grid tariffs. That was going to happen 1st of January this year, but it was postponed because of political noise. But the idea was basically to move to either subscribed capacity or demand charges. So subscribed capacity is basically subscribing to a capacity in advance, and consumption below that limit leads to a very small energy term, which reflects roughly the marginal losses. And whenever you go above the limit, you pay a pretty big excess fee. So it's basically a way to incentivize you staying below your subscribed capacity. But it can also come into the form of demand charges, which is basically a measured peak kind of tariff, which is part of what was proposed by NVE. The idea was to move away from this energy-based, which has like today a flat tariff per kilowatt hour, but it can also be time of use with some time dependency during the day or winter, summer, etc. So now it's a combination of demand charges and time of use that has been decided, but let's see, there's still some political work to be done before they are supposed to be introduced in July. But I didn't care so much about this in my PhD because I want to tackle the idea of grid tariff design in general to also make it relevant for the European audience. The question was like, how much grid tariff, drama can tariffs actually cause? And it turns out it's a lot. So when the suggestions for change came, there was a lot of noise in the media and a lot of the distributed generation people were very unhappy because 1/3 of their business case is actually in saving money when you produce your own PV power. They don't have to pay grid tariffs for that, even though their peak import during the winter is exactly the same, meaning that their costs implicated on the grid are exactly the same. So there was a lot of noise, and there was like a small retaliation from the regulator and some scientists, but not a lot really in comparison. So this is very like a lot of interest, a lot of agendas, and this is also what interests me to dig further into this, to see like who is right and who is wrong and what makes sense to do. So that's sort of the grid tariff part, and now we get into the design. And I tried to make slides on this, but I realized that it would take a lot of time, so I only have this slide, and we can maybe get back more into the details later. But basically, the perfect grid tariff should not only be cost reflective and sort of perfectly reflect the cost of the grid. In that case, maybe you would just use some locational marginal prices or something, but that's not very popular, fair, or easy to do. So basically, to design the perfect grid tariff, you need to think about many things. Maybe you have very high implementation costs of, for example, introducing smart meters. I mean, we have them, but many countries don't. Maybe you need new platforms. Maybe you need real-time information and process on how to give it. The DSOs cares also a lot about cost recovery, because they are very interested in having stable income, not an income that differentiated a lot from year to year. And the consumers are, of course, very into the fairness part. And then the question is, what is fairness? Is it about economic efficiency and cost reflectivity, or is it about not hurting vulnerable consumers, which is a very central part of the EU transition criteria? Complexity is also a big factor, because we want to make it understandable, simple, but of course, the simpler it is, the worse it is, at least sometimes. So we can't just make like this super giga matrix perfect grid tariff design, because no one would understand it, and then it doesn't lead to a lot of acceptance. So that's, yeah, there's a lot of criteria that needs to be taken into account. But I did a lot of research on cost redistribution, so I wanted to talk a bit extra on that part. So recently, actually this week, we had a paper accepted in energy policy, very, very good week for me, where we tried to look into the cost redistribution of subscribed capacity tariffs. And this is something I started to work on back in 2018, when it was still a very hot candidate for the structure to be chosen by the regulator. Now it's a bit less popular, but I still think it's worth doing research on it. So we took 84 customers, and we took 6 years of load data. And the reason we want to do that is because we wanted to look into not only how the cost is distributed in 1 year, but for many years, because in Norway, the annual load and peak loads are very much temperature dominated, and some years are warm and some are cold. And that's why that's important to do. So we actually developed a stochastic method to figure out what you should subscribe to in advance, not knowing how cold or warm the winter will be, by simply putting together a very simple stochastic linear program. And we did that for the suggestion by the regulator, which was sort of a static capacity subscription tariff. But we also looked into this more dynamic version, where you are only kept to your capacity whenever there is scarcity or problems in the grid. We also looked into what happens if you react or you subscribed only using the previous year's optimum, to see like what could happen if you miss. But I won't talk so much about that. I'll focus on the stochastic part. So this is an Energy Systems Seminar presentation, so I need to have some equations. Not sure how easy it is to see, but I'll try. So basically, it's a model that finds the optimal subscribed capacity level under the uncertainty in demand. And demand below the subscribed capacity limit is subject to a low cost, and import above the subscribed capacity limit is subject to a high cost. And also there are just a few constraints to make sure that these costs are properly allocated. And that is the whole thing. It's very simple. It's very few equations. And for the dynamic subscribed capacity, it's exactly the same, except that you have to cut your load whenever you go above the limit, but only during not during all time steps, but only during the activation part, which means that the DSO has sent some kind of signal telling you to stay below your subscribed capacity. So it's not as often, but the cost is a lot higher, and this is based on a value of cut load curve similar that ends up in a value of lost loads fashion. We just wanted to show how are the costs redistributed between consumers when we apply this tariff. Just to see if all the drama that was raised by different people in different lobbyist organizations and politicians. And we see that the cost redistribution, so if you're above one, you're worse off, and if you're below one, you're better off. We see that it's not really that dramatic, and that's actually one of the main results from the paper, is that changing to a capacity-based tariff is not very dramatic for most people. And those who are worse off, they are only 25% worse off, and most stay like inside 10 or even 5% changes in costs. And of course, it differs a bit from year to year, depending on if it was warm or cold or your consumption in general, right? But there is no drama in this, is what we're trying to say. So this was under the static subscribed capacity, but under the dynamic, it gets a bit worse, because if your peak demand is very well correlated with the system peak demand, then you will have a lot of your load curtailed due to the activations from the DSO. And then some consumers were a lot worse off, and some were a lot better off. This is not maybe as robust then, because this would probably create a lot of let's say concerns for consumers. Yeah, this is basically just to show what happens when you apply dynamic, very cost-reflective grid tariffs. So we basically try to do a regression and see how it works. And it turns out that, yeah, the higher load factor you have, meaning that your peak load relative to your average load is very low. It basically means that you don't have very high peak loads. Then your costs are lower. So the trend is sort of pointing the way that we expected it to do. So if you have very high peak loads relative to your average load, then your costs are high. And that is true both for the static and the dynamic capacity tariff. So this is one of the main results from that article. So we see that it's working relatively well. I'm not sure about my time here, but
you have another 7 minutes.
Yes, 20.
Yeah. Okay. So I'm actually moving even faster than maybe I have to, but that's fine. We can discuss, and I have more slides. Here comes another very central part of the research I've done, and that's the importance of coordination. And I mean, I've already spoiled some of it. Basically, we want to know when is the grid actually congested, we just mapped those 84 consumers that were under the same substation, and we checked, okay, so how many times are they close or relatively or above the capacity limit of that part of the grid. And that's shown by these red tops, and this is 6 years of data, right? And it turns out that actually more than half of the hours, this is 1 year over 6 years. And the grid is dimensioned based on the peak load that you have in, of course, the worst year over, let's say, I don't know, 20 or 30 or maybe 50 years. But so if you imagine that the DSO only recovers costs based on those hours that are congested and has problems, right? Then the DSO would have to recover 51% of its costs in 1 out of 6 years. It's not possible, right? We can't do that. So let's say a very, very dynamic pricing law doesn't work because it only fills the cost reflectiveness criteria, but probably none of the other 5 that I mentioned before. So this is also a part of the reason why the results from the previous slides show that some years everyone is better off and some years everyone's worse off. And that's just because some years there were a lot more activations because it was colder and the grid's load was higher. So perfectly cost-reflective tariffs are, they're more cost-reflective, but they're probably not possible to implement, basically. So it's always a trade-off. And some years had very few activations, and then maybe you don't really need a strong pricing signal at all, but you can't know that in advance, right? So coordination is important because we want to target these hours where it's the worst, and those hours where there's not really any problem, we don't really care. So basically, one of the main takeaways I want to give you is that the static price signal can never capture the actual state of the grid. And this is due to the coincidence factor, right? Because if I am billed by my peak demand, and my peak demand is, I don't know, middle of summer or some time where there's no problem in the grid, that price signal is not very effective. And this is actually what's being implemented by NVE now, this demand charges. It has nothing to do with the state of the grid. And of course, the reason they have done that is because it's very complicated to implement and hard to communicate. But it is arguably not very cost-reflective. So I wanted to look into that, and I've done that also with other researchers in SINTEF and in Statnett, and also at NTNU. And one of the main findings we have from several publications is that basically what you need in addition to a static price signal is some kind of coordination, and that's where the local electricity markets come in. Because local electricity markets are an optional, an excellent tool to coordinate resources to make sure that you're actually responding to the real challenge and not just your own little static price signal. But an alternative to coordinating is also using a dynamic price signal, which is actually then sending this real-time information about the state of the grid and giving you a corresponding price signal. So there are a few ways to do this, and I'll get into some results. But I'll try to show the concept first. So basically, this is two consumers. One has a high peak load in the morning, and one has a high peak load in the evening. And this is their aggregated load. So what happens if both of them try to reduce their peak load? And I give them 1 kilowatt-hour of flexibility. It will look like this. It looks reasonable enough, right? They have both reduced their peaks a little bit. But what's the point when the grid still has to be dimensioned for this peak, right? So what happens when they coordinate is that instead of reducing his load in the morning by the first consumer, it will also help the second consumer reduce in the evening by not using his flexibility in the morning, but rather using it in the evening. And then you have reduced the load even further. So that's why this coordination part is very important. And it's important to not only look at what you can do with your own profiles, but more for the system. So that's just a very conceptual illustration. So we tried that in a paper that we published 2 years ago, where we used the static capacity subscription price signal, and we thought that, okay, let's see if they can trade efficiently to reduce their peak loads in the local electricity market. And it turns out it works very well. So basically, whenever someone has free capacity, it can be rented by other end users. So the idea is basically that they should try to share this free capacity by using flexible assets. And that way they can get a better outcome, and the outcome looks something like this. So it's a bit tricky on the screen, I think, but whatever you see this little like flat line here, that's the case with the local markets. So when everyone worked together, they could achieve 20% lower peak load than when no one worked together. So that's why we keep focusing on this coordination part. I also have, this is not published work, but work in progress with Matthias Hoffman at Statnett. And what we wanted to look into is, okay, how well do different tariff structures work on reducing peak loads, but not only on reducing peak loads, but to reduce peak loads in different parts of the grid. Because Matthias is more interested in the TSO perspectives, and what we wanted to see is, okay, what happens in the low voltage grid versus the medium and high voltage grid. And it turns out, and this is only preliminary, there might be slight changes, but the main message is the same. And that's that time of use tariffs are working not very well in the low voltage grid, but it's working a lot better the further up in the grid you go. And that's also due to this coincidence factor that you have different types of consumers. Some are commercial, some are industrial, some are residential, some have electric heating, and some have district heating. And so it's also a question about which part of the grid is currently congested or has a lot of costs connected to upgrading or replacing it. Thank you. You can actually see that different type of grid tariffs impact different parts of the grid differently. So what we're trying to say with this is that if you're a grid planner and most of your costs are connected to the low voltage grid, then you might be better off choosing one of these tariffs. Whereas if your costs are related to the high voltage grid, meaning high to medium voltage transformers or grids in cities, other tariffs might be more efficient. So it's not the one solution for all. So what we see here is that the capacity-based tariffs are working very well on low voltage grids, whereas the time of use ones are not working as well. But it's completely flipped for the high voltage grid. Yeah, that's the end of my presentation. Basically, the main takeaways that I want you to try to remember at least from this presentation is that grid tariffs is definitely not some flat cost that we should put on consumers. It can be used to shape in a relatively undramatic way to have better grid-friendly integration. And for almost all consumers, there is no dramatic change in costs that is stopping us. We shouldn't really, at least that's my argument, that this is not a very good argument for not changing the tariff structure. The concerns for very high changing costs. And we're actually seeing, I have some bonus slides with some references that are pointing out that capacity tariffs are actually not hitting vulnerable consumers more than rich ones, and it's actually more cost reflective. Yeah, and capacity tariffs just, they appear to be better in general, but of course they come with some drawbacks. When it comes to the coordination and flexibility part, basically static price signals are fine, but they're a lot better when you have coordination mechanisms. And different tariffs work differently on different grid levels. And dynamic tariffs are really good on the cost reflectivity part, but they can perform pretty badly on all the other criteria that are required. And local electricity markets might just be the platform to facilitate the coordination that we're talking about. Yeah, and by that, I think we open for questions, and I thank you for listening.